Hey, physics babies. So, this is episode 10 of our pandemic education. And maybe good for you, maybe not so good for you. This is going to be the first assessment that will have an actual grade in PowerSchool associated with it. So, I'm going to highly recommend you take notes and you reach out afterwards if you have any questions or concerns. Today, we kind of have a jam-packed jam-packed lesson. We're talking about series circuits, parallel circuits, and combined circuits. So let's get started. All right, lovelies. So the first thing I want to show you is actually the Word document that I'm uploading as your notes/assessment. So the first bit, we've got room for our first example, second example, and then combined example. All of these I'm going to be doing in the PowerPoint, so feel free to fill them in as you choose. If you want to use the Word document, that's fine. If you want to take your own notes, no worries. The assessment, though, actually starts here. I just wanted to be able to upload one document for you. So it says assessment, series, assessment, parallel, and then assessment combined. As you can see, there's 2 series examples, there's 2 parallel examples, and then 1 combined. And then this is what I am checking. So you are free to actually type into this document, input your answers, and hit submit. Please make sure you hit submit. Those of you that know I'm talking to you, please make sure you hit submit. Okay. The next thing I want to talk to you guys about is to make sure that you make a formula sheet for yourself. I've got my formula sheet right here. Made a nice big one. I will take a picture of it and upload it to Google Classroom as well. If you want to use mine, that's fine. But if you want to make your own, honestly, I would love to recommend it. But otherwise, let's get started. So, Unit 5, this is Lesson 6. We are talking about series, parallel, and combined circuits. So, by the end of the day, by the end of the lesson, you will be able to model series, parallel, and combined circuits and calculate equivalent resistance. You will also be able to complete a VIR table for series, parallel, and combined circuits. All right, so what is the difference between these 2 circuits? For a series circuit, if one light bulb breaks or is removed, what's going to happen? So this picture right here is an example of a series circuit. If this light bulb here breaks, what's going to happen? Make a prediction. So our current's no longer able to flow through this circuit. So my electricity leaves, goes to the first bulb, and then because this is now a broken circuit, it's open, electricity stops flowing. So in a series circuit, your current is the same at all points in the circuit because it's one current going through there. The total voltage will be divided amongst the resistors. So current I1 equals I2 equals I3 equals however many you've got, right? It stays the same the whole way. Our total voltage, however, so VT for total, is going to equal the sum of the other voltages added together. And then our total or equivalence, 2 words that mean the same thing, resistance, is going to accumulate. So that means that we've got these different resistors, and then the resistance for the circuit as a whole will add up throughout the circuit. So we are going to draw a series circuit that has a 12-volt battery, a 3 ohm resistor, a 2 ohm resistor, and a 1 ohm resistor. We are trying to determine the equivalent resistance of the circuit. So this is our first example. Please make sure you are taking some notes or referencing the notes that I posted on Google Classroom for you, okay? So here is a beautiful picture of my circuit. We've got my 12-volt battery. We move to a 3 ohm resistor, to a 2 ohm resistor, to a 1 ohm resistor. And as you can see, there's one path. If I were to somehow do something, and break one of my resistors, the entire circuit would stop working because the electricity has to flow through each piece to get back to the battery. So this is a VIR table. of your table. So remember from, I believe it was last lesson, V equals IR. So I have taken the liberty of starting to fill in this table for us. We've got my first resistor, my second resistor, my third resistor, and my total. My total has to equal the size of the battery that we started with, right? I don't suddenly get more voltage. And then I just filled in the resistance for each of our resistors. We've got one that's 1 ohm, one that's 2 ohms, and one that's 3 ohms. So resistance in a series circuit is additive. So 1 plus 2 plus 3 equals 6. The total resistance of my circuit is 6 ohms. There we go. 6 ohms. Nailed it. Crushed it. We're so smart. All right, now we're going to talk about the total current of our circuit. So going back to our table, we need to remember that V equals I times R. So let's start filling in what we know. For my total, I've got a V of 12 volts. So I've got 12 equals I, which we don't know yet, times my resistance, which is 6. What are we going to do to get this I, my current, all by itself? Hopefully you said divide by 6 because you remember that division is the opposite of multiplication. So we're going to divide both sides by 6. Guys, what's 12 divided by 6? 2. Great job. So my total current is 2 amps. Now, we need to next figure out the voltage drop across each resistor. So remember, the voltage for the entire circuit adds up and will equal 12. But we need to figure out the current first to be able to figure out the voltage. And current in a series resistor is constant. So if it's 2 amps for the total, we've got 2 amps running through each of our resistors. Now let's use that information to figure out our voltage across each. So remember, V equals IR, so we're going to do that 1, 2, 3 times. We've got, for resistor 1, V equals 2 times 1. For our second resistor, V2, we've got 2 times 2. And for our third resistor, we've got 2 times 3. Now, I don't know about you guys, hopefully this is math that we can handle. 2 times 1 is 2. 2 times 2 is 4. And 2 times 3 is 6. We're so smart. And let's take a second and double check. 2 plus 4 plus 6 equals 12. Nailed it. So this is just putting into words our table. As you are looking at problems, you'll see that they have actual questions, right? We take our table and we use the information in our table to answer the specific question. The table is the hardest part, but remember that we're not done just because we found our table. We are done once we officially answer the question that is being asked. So this question asks us to determine the voltage drop. So we would say R1 causes a 2 volt drop, R2 causes a 4 volt drop, and R3 causes a 6 volt drop. And these numbers right here were pulled from our table. So here it is. Easy peasy, easy peasy, easy peasy. Double checking it. Straightforward, you guys got this. I really like series circuits. I think they're very straightforward, and they especially help if you have a handy dandy little section in your formula sheet for it. I'll make sure to post that for you, don't worry. Okay, so let's talk now about parallel circuits. A parallel circuit means that there are multiple paths for the current to flow through. My current will leave the battery, and it can either go through this light bulb and back to the battery, or it could go up to this light bulb and then go back to the battery. So if a light bulb is broken or removed, what do you think would happen to my circuit? take a second and think about it. The current still has a path to go through, right? Instead of my current moving through this light bulb, it's just going to say, okay, here we go. Instead, all the current will move through this light bulb. And then we're good. All right, sorry about that. So as I was saying, the current can still flow through another path. If we break this light bulb is still able to be illuminated because the current will just move through this pathway instead. Same thing over here. If this light bulb becomes broken or removed, the current will just flow through this pathway. All right, so in parallel circuits, the current is split between the two branches. So there is a total current, and we find that total current by adding together the currents from the other branch, from each branch of my circuit. But in a parallel circuit, the total voltage will stay the same at all points in the circuit. Last but not least, our total or equivalent resistance is split. Please make sure you write down this formula. It's a little weird. So our total resistance will equal, I actually have two formulas, write them both down. The first one is 1 divided by 1 over R1 plus 1 over R2 plus 1 over R3 plus however many resistors we have. Or, oh, I'll show you the next one in a second. I'm sorry about that. So as an example, to find the total resistance of this circuit in parallel that's got two 4-ohm resistors, you can take your handy dandy calculator and do 1 divided by, this is where I recommend you maybe use parentheses, 1 divided by 4 plus 1 divided by 4, close your parentheses, and you'll get 2. If you need some help on this, please reach out. I know it's a little weird, okay? But I believe in you. You guys can handle it. All right, so we are going to draw a circuit that's got a 9-volt battery, a 3-ohm resistor, a 5-ohm resistor, and a 6-ohm resistor all in parallel. And we are going to try and determine the equivalent resistance of the circuit. So here is my lovely handy dandy picture for you. I've got my 9-volt battery up top right here. And then we've got our 3 resistors that are all in parallel. So my current will exit, and it can go through one of these 3 pathways before returning to my battery. So our total resistance, how are we going to find it? If we see that we're in parallel, we need to set up that equation. I've written it down here. Here's going to be the final answer that we're going to get. So let's go. So the other formula we can utilize is 1 divided by total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. I'm going to set it up and do the 1 over 3 plus 1 over 5 plus 1 over 6. We'll put all this in parentheses, and we will tippy-tappy-typey this into our calculadora, and you will wind up with this fancy number right here. 3 sig figs is perfect as you are doing any of your answers, so 1.43 ohms is more than acceptable. So the circuit has an equivalent resistance of 1.428 ohm resistor. So it's a little weird, right? I've got all of these resistors that are more than that, right? But because the way the current splits in between those 3 pathways, it winds up having the equivalent resistance of just 1 resistor at this value. Kind of cool, right? All right, next we're going to determine the total current. So going back to V equals IR, helpful hint for you also. If you are trying to do this on paper, I always like to write V equals I times R up at the top. I don't know why this formula sometimes escapes my memory, but it do. So if you remember that these tables are V equals I times R, it just kind of makes life a little bit easier because then you can start looking for your blanks. So we've got this 9-volt battery. We've got this total resistance. Let's find this number right here. We will say 9 equals I times 1.428 How are we going to get I by itself? Well, we need to move this over. How will we do that? By dividing. And remember, whatever you do to one side, you got to do the other. So we'll divide by 1.428. 1.428. These cancel out, and we'll get I by itself, and we will find that I equals 6.30 amps, or I don't know if that's exactly perfect. Hold on. 9 by 1.428. Yeah, right. It's another decimal. It keeps going, and that's why 3 sig figs is always more than enough in this class. Okay, guys? So the total current running through this circuit is 6.30 amps. Question answered. All right, now we're going to determine the current through each branch. So if I have a total of 9 volts in a parallel circuit, remember, the voltage stays the same in each of these branches. So each of these have a 9 volt, 9 volts as their voltage. Sorry, that sounds weird. All right, so again, using our V equals I times R, we're going to set up this equation 3 different times to solve for 3 different currents. R1, we've got 9 equals 1 times 3. For R2, we've got 9 equals I should probably make that capital so it doesn't look like a 1, huh? I times 5. And then last but not least, we've got 9 equals I times 6. All right, we're going to do division on all these to get I by itself. Divide by 3, divide by 3. 9 divided by 3 is 3. Man, I really miss you guys to tell me all the answers. Next, we're doing divided by 5. 9 divided by 5 is 1.8. Awesome. Those go away. Last but not least, 9 divided by 6, because we're dividing by 6 on both sides, because whatever you do to one side, you got to do the other. And we get 1.5. Let's check our answers. Beautiful. We are so freaking smart. And if you were to go through and double check this, 3 plus 1.8 plus 1.5 gives us 6.30. If you don't believe me, check it on your calculadora. And there you have it. So, as a quick recap, series versus parallel. A series circuit, there is only one path for the current to flow through. Everything is directly connected, and the current is constant. In a parallel circuit, we've got multiple pathways for the current to run through that are parallel to one another. And remember, parallel means like they don't touch. Technically, they connect at some point, right? But we can have 2 particles going, 2 bits of electricity going through each of these, and they wouldn't touch each other. And in a parallel circuit, voltage is constant across. So this is where things get a little tougher, but stay with me. You guys got this. I believe in you. What if we have both? So here's an example of a circuit where I have 3 resistors, but we've got 2 kind of options going on here. So we can say that resistors 2 and 3 are operating in parallel from each other because my current will either go through 1, and then it'll either go through 2 and back, or it'll go through 1 and then go through 3 before returning. Remember, there's only one direction of current flow, so it is impossible for the current to go through resistor 1, go through resistor 3, go up 2, and then back through 1, or like up 2 and then back down. Like, that doesn't work. So current will only go in one direction. So we have 2 resistors operating in parallel, but then we also have a set of series resistors as well. So take a sec, pause me, jot down these steps. When you have a combined circuit, you're going to start with the innermost or most complex part of the circuit. If you're not sure what the most complex part is, find whatever is acting in parallel and call that your most complex part. You will calculate the equivalent resistance of that complex part and pretend for a second that it's one single resistor. You're going to keep working outwards to combine more and more resistors. So, looking at this example right here, the complex area that's got things moving in parallel is right here, these two. So what we would do is we would figure out their resistance, and then for a second, to keep making our calculations happen, we'll pretend that it's one resistor, okay? Then from there, right, this is a simple series circuit, and we are good to go. And you can solve that, you just did it, right? All right, so I've got one example, and then you'll be free to try this on your own. Here is our combined circuit example. We've got one 5 ohm resistor, and then we've got a 7 ohm resistor and a 10 ohm resistor. As you can see, I've got the 7 and the 10 ohm resistor working in parallel, right? My current will go through the R1 and then it'll split and either go to R2 and then back, or it'll go through R3 and then back. If you had to guess, which section do you think is more complicated? Hopefully you picked these two that are in parallel, because parallel is always more challenging. So here's my little table. We've got our series and then the two that are in parallel, okay? And we're going to solve for the parallel first because that's more complex. I keep this in a, keep this in a green box and then this in a orange box throughout. So hopefully that will help make things easier. Step 1 is to find the resistance of this more complicated part so we can call it one resistor. So according to my handy dandy formula chart that hopefully you have either made your own version of by now or have printed mine or have mine sitting next to you, I don't know, but hopefully you got this ready to go. The resistance in a parallel circuit, we've got that are, I'm going to call it 2, 3, for the resistance of 2 and 3 together will equal 1 divided by 1 over 7 plus 1 over 10. And I am going to put both of these in parentheses like that and type it into my calculator. You should try this yourself. If you're not ready to, definitely pause me and get a calculator so you can try it. And I'm getting 4.12. We're going to call it 4 ohms today because Miss Pop is a little lazy and doesn't want to deal with 3 sig figs. I want to deal with easy numbers, okay? Okay, sounds good. So now we're going to replace those 2 resistors that were acting in parallel and say instead we've got one resistor right here that's got 4 ohms, okay? And we're just pretending for a second because look, now this is just a simple series circuit. It's easy to solve for. We'll take our resistances and add them together to find the total resistance of our circuit. 5 plus 4 equals 9. We now know that the total resistance of my circuit is 9 ohms, okay? We just did a little bit of addition to get 9, and that's what goes right there. Oops, sorry, I forgot. I keep forgetting what's coming next, even though I just did this. Okay, anyways, now that this is 9 ohms, we can easily find this box right here. Remember, V equals I times R. So 12 equals I times 9. What are we going to do to both sides to get I by itself? Divide, miss. All right, divided by 9. Divided by 9. Those go away. And 12 divided by 9 gives us 1.3. More specifically, 1.3333333. But remember, I said I wanted this to be easy today. So 1.3 it is. Now let's think. What other boxes can we fill in if we have a series circuit based on our knowledge about the current? Hey, remember in a series circuit, in case you forgot, formula sheet, right? In a series circuit, the current's the same at all points. So if it's 1.3 amps here, it's got to be 1.3 amps here. Okay? Check it out. Excellent. Now, this box right here only has this row right here only has one opening. Let's find it. How are we going to do it? Oh, wait, miss. V equals IR. So V equals 1.3 times 5. That's just easy math. Plug it in and you'll get 6.5 volts. So that's where this came from. Okay? Oops, sorry. 6.5 volts. That's where this is coming from. Let's talk about where this comes from. Okay? For a second, remember, we're pretending that this is one resistor. This green box is just the one resistor. Remember that in a series circuit, our voltage adds up. So I've got R1 plus R, we're calling it 2, 3 because we're combining them, 2, 3, equals R total. So 6.5 plus R 2, 3 equals 12. Well, we got to get our 2, 3 by itself. So what are we going to do? Subtract, miss. Remember, subtract. Whatever you do to one side, you got to do the other. So we will take 12 and subtract 6.5. And we get that R for 2, 3 equals 5.5. There we go. There it is. When we have two resistors in parallel, they have the same voltage. So by finding their combined value, we know the value for each of them, okay? It's all the same. And now we're just missing 2 easy little boxes that we will solve for using V equals IR. 5.5 equals I times 7. 5.5 equals I times 10. Do your division, get I all by itself. Check your work, make sure you get my values. That's it. So I know it's kind of a lot. Take notes, watch the video again, come to office hours. I am available, send me emails. I'm here for you guys. I know that this kind of sucks. I know it's a lot, but I believe in you and I know you can do it. I hope you're all doing well, staying safe, staying healthy. If you need me, send me an email, okay? That's it. I love you lots. Bye.